but you know, it will get better. You will see. At the end of the ride, people are typically kind of happy with their performance. Believe it or not. Anything else, folks? You want to get off your chest? Good. All right. Well, let me remind you why we're all here. First of all, you got to pass this class for your grade, for your degree, so that's one. Second is that what we're trying to do is to really find a good description of atoms and molecules from the bottom up, okay? Things that typically in most other classes we simply gloss over and just apply a couple of tricks that are listed. You have to do this, this, and this, and then everything will be okay. Here we're trying to figure out why are those things correct or why not. Okay, so really the physical underpinnings of these descriptions. Where do they come from? Why are they valid? Those are very important questions, folks. You should always ask those questions yourself. Don't always just assume that what people have said is true. You gotta really convince yourself that this is the way it is. So we were on our way doing that up to the quiz, and now we're going to continue that. Okay, so what did we do last Wednesday? Let me remind you, we were introducing a two-dimensional wave on a sphere, and we noticed that the solutions, the wave functions that follow from solving the Schrödinger equation for that particular problem, those wave functions already start to look a lot like the orbitals that we know, okay? And it has everything to do with the fact that the atom is a spherical system, it has spherical symmetry, and therefore it must have the character of those solutions. But it's not the only thing, because we forgot one important ingredient, and that is the description of the wave function along the radial coordinate, okay? Because if you want to describe three dimensions in spherical coordinates, you have to describe the sphere and the radius of that sphere. So you can make a small sphere, a big sphere. That's how you describe the whole space. We didn't do that on Wednesday, so that is up for today. So I only have 5 slides today, but don't be fooled. They are intense. Okay? So what I'm going to do is I'm going to show you how you get the solutions for the so-called radial part of the atomic wave function. Okay? The radial part of the wave function, that's what we're focusing on today. I'm going to go through some nitty-gritty. I'm going to show you how to do that. I'm going to show you that this is really the way it is. Do you have to remember the derivation I'm going through today? The answer is no. You don't have to remember every step. I just want to show you that this is all sound and it can be done. I want you to be able to work with the results, okay? This is just a little preemptive warning. Don't freak out by the math on the slide. Just be able to appreciate where the math comes from, and the results at the end of the ride are things that you can use and implement. Okay, so next time you see a result like that, you feel like, oh, okay, it doesn't fall out of the blue sky. It actually comes from somewhere. That's what we're trying to do. Okay, so here is now, again, a spherical system, but I'm going to be a little bit more specific, because I'm going to put a plus sign at the origin of this sphere, which is, of course, the nucleus, and then I have a negative sign, that is the ME, that's the mass of the electron, that sits somewhere a distance away from it. Okay, I'm going to use my spherical system again to try to capture this problem. If I use spherical coordinates, then of course I have 3 coordinates, r, which is the radius, and then theta and phi for describing the sphere. So, but what if I have now my complete atom? And of course the atom that we're going to talk about is the hydrogen atom, which has 1 proton as the nucleus and 1 electron as the electron that is swirling around. That is our goal, okay? So we want to describe that. Now, an important ingredient is that there is an interaction between the nucleus and the electron, and that's simply a Coulombic interaction, okay? An electrostatic interaction. Plus and minus attract, because they're charged. And this V of R is the potential of that attraction, okay? What you can see is it scales as 1 over R. That is a Coulombic attractive force between oppositely charged particles, 1 over R. And then there's a couple of constants in there. Let's walk through those. Z is simply the charge of the nucleus, okay, which is 1 in the case of hydrogen. So that's simple. E squared is the square of the electron charge, okay? 4 is a number, pi also a number, and then this epsilon 0, which is the vacuum permittivity, which is one of those fundamental constants that pops up everywhere, okay? But the bottom line is those are all constants. You can just write them down. There's no mystery there. This 1 over R is the most important thing because it tells me that this potential is changing as I move along this R coordinate. Okay, now remember, we've talked a lot about potentials already, barriers, and harmonic potential, right? But this is the potential that we really have to worry about, because this is the potential that is active in the atom. So that is basically our task. Can we solve this problem? The potential is not the only problem, turns out, because if I'm writing down this Hamiltonian for this system, I'm going to see a couple of things in there. There is always going to be a kinetic energy part and a potential energy part. Now, that potential energy part is all the way to the right. That is my potential, right there, okay? And those first two terms is the kinetic energy, but there's two. Why? Because I have two particles. I have a nucleus, which is a proton, and an electron, which is my second particle. So I have two of these funny little triangles, the del squared, which is basically the second order derivative in 3 dimensions, as we have seen before. Okay, so we have a part for the nucleus, which is labeled as del squared Rn. That is the kinetic energy of the nucleus, and then the kinetic energy of the electron, which is described by del squared Re. Okay? Again, if you've never seen this before, it looks pretty terrifying, but you just have to learn what it means. Okay? The first term, kinetic energy of the nucleus. Second term, kinetic energy of the electron. Last term, their mutual interaction. That's it. If I solve this problem, I solve the entire thing. But I don't like this because I see two coordinates. I see coordinates for Rn and Re, and this R in the last one is basically the difference between the two. This is going to get complicated pretty quick. So I would like to simplify this problem. How? By doing so-called separation of variables. Okay, what does that mean? That means that there is motion of my atom as a whole, you know, going through space like that, the whole thing. And then, of course, there's also motion of the electron relative to the nucleus. Okay? Of course, I'm interested in the motion of the electron relative to the nucleus. I'm not interested in the whole thing going through space. That part I don't really need. I'm going to try to describe those two types of motion. That's what I'm trying to do. The first one is the total mass. I'm going to add up the masses of the electron and the nucleus, and I'm also going to determine their center of mass. Okay, so the center of mass is the center of mass of the entire system, and that system is moving around. Okay, so this R is now the coordinate of my entire system. M, big M, is the mass of this entire system. So I have a particle that is the whole. I just squeeze my eyes and pretend there's just one particle. It's not two, it's just one, and this particle moves through space with these coordinates. M is the mass, R is its position in space. Clearly, I'm not really interested in this part, okay? I'm interested in the second part, which is the reduced mass. The reduced mass is kind of like the combination of the two, okay? it's defined in a different way. 1 over the reduced mass equals 1 over the mass of the nucleus plus 1 over the mass of the electron. This is a very common way for describing a reduced quantity of 2 ingredients, right? And in this case, it's for our system, the hydrogen atom. There's a reduced mass. There's also a reduced coordinate, which is basically simply the difference between Re and Rn. Okay? It's the relative position of the two, just the distance between the two particles. It's just the distance of the electron relative to where the nucleus sits. So I have 2 coordinate systems. One of them is a system as a whole on the left. The second one is basically the relative motion of the electron around the nucleus. This is the part that I want. And so what I'm trying to do now is taking this Hamiltonian and writing it in terms of the reduced mass and the relative distance. And so what I can do is I can take this part, the kinetic energy. The kinetic energy part is of relevance because the last part, potential energy, already depends on this R, which is relevant. Good, that's taken care of. So the kinetic